Welcome to Maths with EJD. In this video, still on mathematical induction, our question is to prove the divisibility of x raised to power 2n minus y raised to power 2n by x plus y. So in short, we have to prove by induction, prove by induction, prove by induction that x raised to power 2n minus y raised to power 2n is divisible by x plus y for all n greater than or equal to 1. That is our proof. That is what we are expected to prove. Okay. And then, of course, you know how we outline these things. We have a claim here right now. The claim is this, that x raised to power 2n minus y raised to power 2n is divisible by x plus y for n greater than or equal to 1, for all n greater than or equal to 1, all. So that means for 1 upwards, for all natural numbers. Of course, that's what mathematical induction is about. So let me sometimes I don't know what to choose. Okay, let me alternate between blue and this. Okay, so the first thing we want to do is the base step. Let's do the base step. So for the base step, we can take at n equals 1, right? At n equals 1, what do we have? We have x raised to power 2 into 1 minus y raised to power 2 into 1. And that is equal to, of course, let's just try this. Let's just say over x plus y, straight up. So you have x squared minus y squared all over x plus y. And this is difference of two squares. Interesting. For difference of two squares, x squared minus y squared is the same thing as x minus y into x plus y all over x plus y. And what do you see? X plus y is right there, cancelled out. So you have x minus y. So you see that for n equals 1, the claim is correct. And of course, we can take it further, right? We can take it further. We can take it further to say at n equals 2, we also get the same thing. But of course, we don't need more than n equals 1. So we can just keep going like this. Okay. So, or maybe I'm tempted. I don't know what to do. Okay, let me just do this. So at n equals 2, right? Yeah, it means you have x raised to power 2 into 2 minus y raised to power 2 into 2 all over x plus y. And that is the same thing as x raised to power 4 minus y raised to power 4 all over x plus y. Of course, this is difference of two squares. So that's like x squared minus y squared into x squared plus y squared. Okay, all over x plus y. And then we still go. So this is another difference of two squares. So you have x minus y into x plus y. That's for this part now. Then this one remains what it is. So you have x squared plus y squared all over x plus y. Interestingly, x plus y still cancels out. So you have x minus y into x squared plus y squared. So that's sweet. So we can say, therefore, the claim is true. The claim is true. The claim is true. Is true. The claim is true for the base step. For the base step. The claim is true for the base step. So let's go on to talk about the inductive hypothesis. So what is the inductive hypothesis now? Inductive hypothesis. So we assume, right? Assume the claim, assume the claim is true for n equals k. And all we can do there is to say that x raised to power 2n minus y raised to power 2n is equal to, let me say is equal to a capital A multiplied by x plus y. You remember everything we've been having in the two base example for base step, right? You see x plus y emerges, so we can cancel out. Same thing here, x plus y emerges. So if it is going to be true for n equals k, so it means you are going to have a particular integer a multiplied by x plus y. So don't forget where a is an integer, okay? So the key is that you have this x plus y standing out right there. Okay, so so that takes us to the final fight, the last fight, like they say. That's the inductive step. The inductive step. So at the inductive step, now we want to prove that the claim, that the claim is true. That the claim, that the claim is true for n equals k plus 1. And that means that now, I mean, don't forget this. This is always helpful. Oh, I think I made a mistake here. This should be 2k, not because you're assuming for k, right? This is 2k, 2k. Yeah. So x raised power 2k minus y raised power 2k should be a into x plus y. So, but this is very important in this final stage we are coming to. So to prove that this claim is true for n equals k plus 1, so that simply means that instead of x raised power 2n, so you are going to have x raised power 2k plus 1 minus y raised power 2k plus 1. Okay, so, and that means we have x raised power 2k plus 2 minus y raised power 2k plus 2. So that is also to say that you have x raised power 2k multiplied by x squared minus y raised power 2k multiplied by y squared. All right, so we have we have what we have here, right? Now, here we need to make we need we need to make a smart move. If you add 0 to something, nothing has changed, right? And one way to add 0 is add something and subtract that thing. So the reason why we want to do this is because we need to balance this out. So what I'm going to do is, okay, let me change the marker here to show that we are going to make a smart move around here. So here, what I'm doing is this. I have x raised, okay, the pattern is easy. Just add x raised power 2k, x raised power 2k y squared, add it and subtract it at the same time, or subtract it and add. That means you have x raised power 2k times y squared minus x raised power 2k y squared plus x raised power 2k y squared, then minus y raised power 2k y squared. Technically, this is 0 because it's exactly the same thing. And the reason we are doing that is we want to be able to factorize out x raised power 2k so we can have x squared minus y squared in brackets. And once we have x squared minus y squared, we can easily have x plus y like we had before. So that's the smart move we just make here. You have x raised power 2k, you have y squared. So that gives us a clear as to. So product of x raised power 2k y squared will help you to be able to factorize x raised power 2k so you can have x squared minus y squared in brackets. That's the purpose of that. So okay, I think I'll go back. So that part is just to show that we did some smart move. So here now we can take out x raised power 2k into x squared minus y squared. X raised power 2k is out now. You have x squared minus y squared in brackets. And here, what is common is y squared. So you have y squared plus y squared into x raised power 2k minus y raised power 2k. Interestingly, right, this looks like something you have seen before. It looks like what you have at the inductive state, which is actually this a into x plus y, right? So, I mean, that is looking interesting already. So that means you can go and say this is x raised power 2k into, this is difference of 2 squares. So you have x minus y, x plus y, all right? X minus y, x plus y. Okay, so you have that plus y squared now. And of course, you don't forget that this is the same thing as a into x plus y, right from our inductive hypothesis. So we just invoke that now. So we basically have, so x plus y is now common. So you have x plus y out here into x raised to power 2k into x minus y plus a y squared. So, I mean, every other thing inside, we don't have a problem with. So you see now that x, so we can see that x raised to power 2k plus 2 minus y raised to power 2k plus 2 is exactly the same thing as x plus y into x raised to power 2k into x minus y plus a y squared divided by x plus y is possible, right? Divided by x plus y. So because this cancels out, and all you have is x raised to power 2k into x minus y plus a y squared. So, I mean, you have that x plus y standing out. So at this point, you can you can come back to your conclusion. So you can conclusion, since since the claim is true for the base step, for the base step and the inductive step and the inductive step and the inductive step, then it is true. Then it is true for all n greater than or equal to 1. And that is how that goes. So thank you so much for listening once again. Be sure to subscribe, hit the notification bell so you can get alerted whenever a new video is released. Comment, like, share. There are many people that would need this. See you in the next video. Thank you for listening.